In this lecture, I will talk about the argument principle. So consider a closed contour here, which we call gamma. And suppose that we have a function f of z, which is analytic in the neighborhood of this contour and also different from 0 there. And inside the contour, we suppose that f is meromorphic. Which then simply means that there can be a finite number of points where the function has poles. And of course there can be zeros here inside also. And what does the argument principle say? Well, the argument principle says the following. We consider the integral around this contour in, let's say, in the positive direction then, of f prime divided by f itself. And then we divide by 2 pi I. And the argument principle says that this integral is actually equal to the number of zeros of f inside. So there could be some zeros in here. And they are counted with multiplicity then. So if we have a double zero, you count it as 2 here now. And then you subtract here the number of poles. And they're also counted with a number of, the order of the poles. So if you have a pole of order 3 here at some point here, then you count it as -3 in this expression then. So this gives you a nice connection between the behavior of the analytic or meromorphic function on the contour then and the number of poles and zeros inside. And this is actually not at all difficult to prove. So what do you do? We start from this contour and then we can of course deform it so that we get around each one of these poles or zeros we get a small circle here now. And they will be oriented in the same way. And inside each circle there will only be 1 zero or 1 pole, which you can of course achieve because they will form a discrete set. And if we now prove this principle for each one of these small circles, then we can simply add the result from all these small circles. So on the one hand get this contour integral on the left hand side, and on the other hand we will get this then. So it's actually enough to consider the argument principle for a small circle and a function with just 1 pole or zero inside. We can assume at the center also. So suppose that we have this point z0, which is either a zero or a pole. Then we know that we can write f of z in a neighborhood of that point, actually in the whole interior of the corresponding circle, then as z minus z0 to the power m times another analytic function h here now. So, and it's important to note that we can assume that this function h is different from 0 in the interior of the circle. And if m is positive here now, then this is of course the case when you have a zero of order m. And if m is negative, it's the case when you have a pole of order m. So we can actually manage both cases at the same time here now. And of course, m cannot be 0 because then you don't need to consider this circle at all because you don't have points or poles there. So we assume that the function looks like this, and we simply compute the integrand over here. So start by f prime, which is then simply m times z minus z0 to the power m minus 1 times h then. And then you get z minus z naught to the power m times h prime. And if you now divide by f, then you see that if we divide this expression by f, then the h will cancel out and we're just left with m, and this factor will also cancel out against this. There will be just one factor left here now, so you get m divided by z minus z naught here, and up here this whole factor will cancel out against that, and you will be left with h prime of z divided by h of z. So what happens now if we integrate this? Well, if we integrate and multiply by 1 over 2 pi I, in the left-hand side, we of course get this expression that we have in the argument principle. Here, well, this is now a standard integral, which we have done several times to integrate this function, say a constant divided by z minus z naught. And we know that the result here will be m times 2 pi I. But then we divide by 2 pi I also. So we're actually left with m. And this term, when we integrate it, since this function is actually analytic in the whole interior of this small circle, because h is different from 0 there, then by the Cauchy integral theorem, this term will just give you 0 now. And then you see that we computed this expression and we got exactly m, which is what the argument principle states in this case. So that's the whole proof, really, of the argument principle. But there's one thing left to discuss about it. So why is it called the argument principle? That's really the interesting point here now. And the reason is the following. If you consider this integral now of f prime of z divided by f of z dz. What happens when you integrate this in general? Well, there is an obvious primitive function here. So you get the logarithm of f of z here now. So if you integrate this along some curve, gamma, then you will get first of all, here you have the real part of this, which is then the logarithm of f of z absolute, and then you get this argument of f of z here now. And then this should be evaluated at the starting point of the curve and the end point of the curve, like this. So what happens now if you integrate this expression along a closed curve? Well, when you have passed around the whole curve and got back to the same point, of course, this term will not contribute anything, because the value of this will be the same at the starting point and the end point. But this term is different because the argument is actually a multi-valued function. So you could get 0 here also. In the case where, so to speak, the values of f along this curve does not pass around the origin. But if the values of f in the complex plane pass around the origin in the positive direction, then this will give you a contribution here of 2 pi I. And if it passes 2 times around the origin, then it will contribute with 4 pi I, and so on. And if the values of f along the curve will go around in the negative direction, of course, then you get minus 2 pi I. So this integral really, which is the same that we have over here, except for the factor 2 pi I, it really measures how the argument of f changes along the curve gamma. And what the argument principle says is that this change is actually measured by the number of zeros and the numbers of poles of the function. The argument principle has many consequences. In this lecture, I will just talk about one of them, which is the Rocher theorem. The Rocher theorem then starts with, we consider a closed contour here, gamma, and then we have two functions, f of z and g of z, which are analytic on the contour gamma and inside them. We suppose also that we have the following inequality. Absolute of f of z minus g of z is strictly less than absolute value of f itself. But not everywhere, but on gamma. And the conclusion of the Rocher theorem is then that then f and g have the same number of zeros inside this contour. Well, so how do we prove this? Well, the idea is that we consider the function capital F of z, which is then g of z divided by f of z. And this function is then obviously meromorphic here inside. It will have poles exactly at the zeros of f then. And it's also clear that both these functions will be different from 0 on the contour itself, because if g is 0, you would get equality here. If f would be 0, then the right-hand side would be 0, and this is greater than or equal to 0, and this is not possible then. So this is really a function where we can apply the argument principle. So we start then by computing f, capital F prime divided by capital F, which is then equal to, we start by computing the derivative of this, with this is f prime divided times g minus f times g prime, and then divided by f squared then. And down here you will get g divided by f. And then you see that the first term here, when you cancel out the g, you will be left with f prime divided by f. And the second term here now will give you, when you cancel out all the f's, you will be left with g prime divided by g. So if we now integrate here now capital F prime divided by capital F along around this contour, this will be equal to the difference between the corresponding integrals here. So you have first 1 over 2 pi I, and then the integral of f of z divided by f of z dz, and then minus the corresponding integral of G here now. And then we see that according to the argument principle, this first integral here now is exactly the number of zeros of f, which I can then denote, in this I denote it by n naught of f. And this second term here, sorry, it should be the I, is equal to the number of zeros of g. We see that here in the right hand side will give you the number of zeros of f minus the number of zeros of g. So what we want to prove is that difference is 0, which would then mean that they have the same number of zeros. And to prove this, it's enough to prove that this integral is 0 then. But this now follows again from the argument principle in the following way. You see, if we take this inequality here now and divide by the right-hand side, then we see that we'll get 1 minus g of z divided by f of z absolute here always less than 1. Or, in other words, that absolute of 1 minus f of capital F of z is less than 1. And what does this say then? Well, if you take a look in the complex plane here now, you see that this, if you draw the circle around the point 1 here now with radius 1, then we see that all the values of capital F will lie strictly inside this circle here now. But remember, the argument principle says that you can only get something different from 0 here if the values of f, capital F, will wind around the origin. But in this inequality shows that this is impossible. You can never go around the origin if all the values here lie in the right half plane. So that's really the proof of or the idea of the proof of Rocher's theorem. So let me now show you how this can be applied. So consider now the following example of Rocher's theorem. So we consider the polynomial g of z, which is equal to 2 times z to the 5th minus 5 times z squared plus 43. And we put this polynomial equal to 0, and then we ask how many of the zeros of this polynomial will lie inside the disk z absolute less than 2. So we have this disk here now with radius 2 around the origin, and we want to know how many of the zeros of this polynomial lie inside here. Of course, since this is a polynomial of degree 5, we know that there are 5 zeros in the complex plane, but from the start we don't know how many of them will lie inside and how many outside. So the idea is now that we introduce a function f of z, which is then 2 times z to the 5th. And this is a function where it's very easy to see how many zeros it has inside this circle, because there's just 1, of course, at the origin, and it has multiplicity 5. So what we'll do is that we compare these two polynomials now. So we can start by considering the difference now, f of z minus g of z absolute then. So if you from this subtract this, then these two terms cancel out and you get 5 times z squared minus 43. And by the triangle inequality, of course, this is then less than or equal to 5 times z absolute squared plus 43. And on the boundary here where z absolute is equal to 2, you see that you get 5 times 2 squared 5 times 4, which is 20, plus 43, which is 63 then. If we consider f alone, absolute value here now, you see that this will be then 2 times z absolute to the power 5, and then on this boundary, this will be equal to 2 times 2 to the 5th, which is 64. So since 63 is less than 64, we have that this expression is strictly less than this one, which means that we can apply the Rocher theorem and conclude that G has the same number of zeros inside this circle as F has, which means then that G has 5 zeros inside. Now this we will compare with the second example here now. So in this case, let G of Z be equal to Z to the 5th minus 4 times Z to the 4th plus 4 times Z squared minus 7. And again, we put this equal to 0, and we ask the same question with the same circle here now. How many zeros of this polynomial lie inside this circle? Well, in this case, it's no good idea to compare with f to the 5th. So what we'll do instead is that we put f equal to z to the 5th minus 4 times z to the 4th. And then we consider again this difference now, f of z minus g of z absolute. So if we subtract from this expression, then we'll get minus 4 z squared plus 7 absolute then. And by the triangle inequality, this will be less than or equal to 4 times z absolute square plus 7. And on the boundary, this would be 2, so you get 4 times 2 squared, which is then 16 plus 7, which gives us 23. On the other hand, if we consider just the absolute value of f itself, then this is equal to absolute value f to the 5th minus 4 times z to the 4th. And here we should now apply the inverse triangle inequality. So let me just rewrite this as absolute value of 4 z to the 4th minus z to the 5th. So I just multiply this by minus 1 then. And then we see that this is larger than or equal to the absolute value of this first term, which is 4 times absolute of z to the 4th. And then minus absolute value of z to the 5th here now. And on this boundary then, you see that this term is then 4 times 2 to the 4th, which is 16 then. And this term will be 2 to the 5th, which is 32. And so this difference is 32 then. And since 23 is less than 32, again we can apply the Rocher theorem to conclude that G and F, they have the same number of zeros inside this circle. But in this case, you see, you can factor F like z to the 4th times z minus 4. Which means then that you see that you have 1 zero of f which lies outside at the point 4 here. And just only 4 of them will lie inside. We have this 0 at the origin, which is multiplicity 4. So the conclusion of the Rocher theorem is then that, again, these two functions will have the same number of zero inside the circle. That is, in this case, 4. So the conclusion is that one of the zeros of G must also lie outside, and only 4 of them will lie inside here now. So G has 4 zeros inside this circle.